Okay, perfect.
If any of you still can't see it, you should always go to the person who's presenting and the people thing on the right side, and you should just pin them. So that automatically makes sure that there
Okay.
is a visible screen. Yeah.
So I have something like this. Let's. Okay. So basically, what is basically happening? Let me zoom out so you can see clearly. So what is happening here is, I have a big function. Okay, it is damping out. So in a physics term, it's damping out. And Ashwin, like, you are a physics student or bachelor student. Like, what is your domain, so that I can give an example in that domain, so that it will be helpful for all. Because I know about Chaitra, Jaitan,
Physics.
Vishal, and then physics.
I'm
Okay,
also physics
perfect.
student.
Okay. Okay, perfect. So we can think of this like this. So imagine that there is a ball you throw up, okay? And under the consequence of gravity, of course, whatever goes up has to come down, unless you are throwing up with a speed of more than speed of escape gravity. So it comes down, it bounces until it reach a point where it loses all its kinetic energy. You know how the physics work. Like, for example, here all the kinetic energy is lost, and also all the potential energy is lost, due to the mere fact that we have air resistance and basically damping due to a lot of factors, of course, right? So we all know that story. What I want you to imagine right now is this. Close your eyes. Let's say I am looking closely only at this particular graph, from 0 to 50. Okay, that means from this point to this point in x-axis. And the ball, I just started now. I just throwed, let's say, a length of 8 meters, and then it comes down, and then it goes down slowly. It's going down. Okay. Now, what I want to do for you is this: close your eyes and think. Uh, the ball is right in front of you. What you have to do is you have to open your eyes every 2 minutes, okay, or 2 seconds. Okay, what do you see? So you are looking at this graph, but not when the ball is moving, but not continuously. You open your eyes every 2 seconds and then see where the ball is. Okay, and then did you imagine this, guys? This has to be very, very interactive, otherwise this lecture
Yes,
is
yes,
not working for sure.
yes, yes.
Okay, perfect. So now, if my guess is correct, what you are looking at is this. When you first open your eyes, you're looking at this. When you second you open your eyes, you're looking at this. And third, let's say this, 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 sorry, yeah, this, and so on. So you will tend to think that the problem here is not that ball is going in a some way, but your perspective says that ball is going in a straight line. Correct,
Yeah.
but never bouncing at all, right?
Okay.
So what you do basically now is, you come to a conclusion that my perspective is right. So the ball is moving in a straight line exactly towards my right side. Clear cut, we come to this conclusion. So this was actually one of the problems in 1600s. Okay. And then so I'll explain you also in a different way. Let's see this in a different perspective. The first perspective is this. Now what I want you to do is do exactly same thing, but now open your eyes every 1 second. Okay, imagine that for a moment. And now what you would see maybe is something like this. Shh. Here, 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 and something like this. So now your perspective has changed completely. You can say that, okay, now the ball is not really moving in a straight line, but in fact it's moving in a direction, but it's not moving in a straight line for sure. But still, it's a very, very zigzag. You see, it's like this. Array is better, right? This, like this. And then you say something like this. So the ball is moving like this. It's very, very random. Again, what you do is, you know where this is going already now. So again, what you do is again close your eyes, but now do it for a lesser and lesser and lesser and lesser time step. At when you continuously open your eyes, that is exactly when you can see the whole ball bouncing. Otherwise, you are really missing out a hell lot of information, right? So this was the idea, kind of motivated Newton, but in a different way. Okay, this is one example. Okay, for now, let's forget about this. Okay, now let's go to the idea of Newton. Newton was of course, he's a great guy. So what he did is he wanted to find out what was exactly happening. So he told to himself, okay, let's say something like this. I am going from my home to some place to buy some food or whatever. Okay. Now I am riding a bicycle. I want to know how much time does it take for me to go from A to B. Okay, simple. In this case, you all know the formula of physics. S is equals to V into T. That means you calculate what is the velocity, and then you say, okay, that means the velocity is equals to the time consumed. So you just note the time that way at which you reach from point A to B, and then you say the whole distance traveled is equals to V into T, and then you're done. Right? This is exactly what we do. Now, remind me this one when we discuss about when we do the definition of derivatives. In case if I forget, okay, because there is a very interesting, just exactly with this formula, S is equals to V into T, and how we can use the derivatives to visualize that. Okay, so after this, so this one is a straight line. Is very simple. Now the problem was not a straight line, but let's say a curved line. Like, just for an example, I take x square. Okay, okay, this is in the okay. I take an x square. When I have something like this, where my speed, y-axis is the x-axis is the speed. Okay, where my speed is changing regularly. So this kind of motion in physics we classify as non-uniform motion, right? In the basic mechanics concepts. So what he came up with is an idea of instantaneous and average speeders. He told, if I calculate a position, if I want to calculate what is the distance traveled from A to B, or even the velocity of A to B, the easiest way is find out the distance and divide by time. So that will give me an average velocity or average speed. Velocity is a big word, I know that, but still, let me use velocity for now. Because speed, okay, I know the difference between speed and velocity. Right now, I am using velocity for a particular reason. Let me do it this way, and then we can change it into speed. Okay. So, right, velocity, he told there is a possibility that we can do all this by calculating instantaneous velocity. And then he thought, if I can find instantaneous velocity, then I can define non-uniform motion. The reason why he was doing this was basically because he wanted to know how Mercury and Venus was going around the sun. This is a very nice one. For example, okay. So when you see the how a relative position between Earth and Venus goes around the sun, it kinds of create a pattern like this,
Project.
which is very intriguing. Maybe this is more nice. So now this is completely non-uniform motion, and he wanted to actually understand this. And this is between Earth and Venus as well, but from the perspective of Sun. Okay, so all this kind of stuff he wanted to understand, and then he had no clue how to do any of them. So he thought, okay, maybe if I try to see what exactly happens with respect to the instantaneous and average speed, uh, we can try to find out something. So he came up with the concept of derivatives. So what he did, we all know. So he told, if I have something like this, okay, okay, if I have something like this, let me try to explain that with a simple straight line, and then we can go for the higher ones. So what he did is simple. He told, let me do something like this. I try to draw a line from here to this point. Now we are looking them as a functions. Okay, let's call this our baseline. So, and the black one is the f of x, the function f of x itself. So now he told, let's do something here. I'll add another line, maybe here, and then now the distance between D and F, okay, if I calculate what happens between B and E, so basically in terms of instantaneous and average velocities, if we talk, then what he did is, instead of going from A to E directly, can I go from B to E, which is a smaller distance, and calculate what is the average velocity, which is very simple. How do we calculate? df divided by B into E, right? That's how we calculate the average velocity. It's basically from the same formula, S is equals to V into T. Now, he told, if I try to reduce this distance between D and F, okay, that means if I try to reduce this distance, now E is also reducing, and he told, when I reach exactly D is equals to F and B is E, at this point of time, I know what exactly is my instantaneous velocity rather than average velocity. But in order for that, we need the concept of limits. That means the distance df is going to 0. To put this in a perspective, mathematical perspective, he did something like this, which we all know. He told, okay, when can I see the average velocity? I mean, how can I convert average velocity t into instantaneous velocity? We have a function f at a certain point, f of x plus h, and minus f of x. So if you want to see this one, what is f of x plus h minus f of x? It's the distance between these two, right? This is my f of x. This point g is f of x, right? And then this point is f of x plus h, right? The distance between g to 0 would be f of x. Distance between h to a is f of x plus h, correct? Now he told, if I try to do this, and as h goes to 0, h and g will collide, and that's when I know what is my instantaneous velocity. Exactly as this one. Did you get it? Is this clear?
Yeah.
And h is, of course, this distance, right? The distance between D and F. So it's very straightforward relation. But in the linear equation, there is actually nothing to do here. Like, it's very, very clear. Like, I think even before that, everybody knew it. But the problem comes when you have something like this. Because straight lines are really, really nice one and easy ones. When I have something like this, it's incredibly hard to find out using the normal method of s is equals to v into t. Now we need something else. So he told, okay, since I have linear equation and I know how limits in linear equation work, can I exactly apply the same thing to to the um, to the parabolic equations? And the answer was yes. There is a nice nice thing. Let me show that to you. Okay, the first one. Where is the meetup here? Look at this. Okay, this is what we were talking about. Open this. You can click on this. So y is equals to x square line, and h is now the distance between this. So this is clearly here. 1 to 3 is the h, and opposite side also, because this is very important to define opposite side as well, because otherwise we will see that we will, if we don't have negative also, we will face a hell lot of problems, which I'll show you immediately after this. Did you open this? Okay. Now if you reduce the h, what is happening is it's going to 0, 0, 0, 0, 0, 0. At x h is equals to 0, we have the instantaneous limits. This is what we were talking about. And Einstein's insights was very nice, very helpful. So the reason why I told you, it's because of this. When you have absolute value of x, this is not defined, because if you see the left and right, you will have a problem. They are not same at zero. Sorry, you want at zero. I can just shift this. Okay. Now, if you see here, even though h is not zero, if you connect them together, it's always zero. So this is a big problem. If the point is not, if the point is not differentiable, like we will come to the differentiability much later. So this is a problem why we need limits from both sides,
What is
right?
h? Can you repeat?
H is the distance between. So in this graph, okay, in this graph, the DE is the H, right? But
Yeah.
uh, in this graph, the between 2 and 1, like for example, if I'll just keep it 1, so that, okay. Now the point I am looking at is exactly at 1. What happens at x is equals to 1? Now the H here is plus 1, which is 2, the dotted line here on the left, on the right, and another one is on the left you cannot see because it's merged with the x-axis.
Yeah.
So this will be a problem, because if I don't have, let's say something like, let's say for example, if I have x square, I have no problem, if you see. So even if I change the value of h,
Yeah.
still working, right? The value of the if you connect the line between minus h to h, the value is exists, the value is not zero. And the why do we need this value? Because this is basically f of x plus h minus f of x, like this value, f of x plus h minus f of x value is this one. In our case, it's the one represented by the orange line.
Okay.
But that value, if it's zero always, as in this case, absolute value of x, if
More
it's
is not.
zero always, so in this case it's zero, right? Doesn't matter what I change the h, it's always zero. In this case, the limit is always zero, no matter what.
Okay.
Doesn't depend on the h. So this is a problem. So we need to take care of this one. We will see that in a moment. Okay, so you get the idea of what Newton was doing as a rate of change of intervals, a rate of
Yeah,
change of all these things, right?
Yeah.
Let's
correct.
drop this for a moment. I still don't want to define, let's say, derivative and what exactly is derivative doing here. Before that, let me give you another example. Let's say, for example, like where is this rate of change used basically? If you see how the growth of virus happens, that's still a rate of change. For example, our coronavirus situation where we are right now is basically because of the same thing, right? It's basically rate of change, and it has to do something with the derivatives. And then also, like for example, if you just mix two liquids, doesn't mean not necessarily water, or if you mix sulfuric acid and some other acid, it will create some reactions, and all those reactions also has to do a lot with the derivatives perspective. Okay, so now velocity, of course, you know how Newton derived in this way. I'm sorry I couldn't prepare it much before, I'm just typing it here. If I have a function s is equals to f of t, then what happens is basically I want to calculate what is the delta s. Oh, by the way, guys, Overleaf is giving a free premium upgrade to everybody for a month. So if you're using Overleaf, feel free.
Oh, really? Okay.
Yeah. I have a now right now I have the premium one. They started yesterday. Okay, f of t plus h minus f of t. Correct. I'm writing for the s is equals to f of t function, or s is equals to v into t. Correct. And then I see the delta s. So the average velocity v would be, okay. It will come here. Just a wait. So we have something like this, right? Like this. I have a function s is equals to f of t. This is purely physical perspective. It has nothing to do with the derivatives right now. And I see delta s, which is this, and velocity is calculated by the rate of change of distance divided by the rate of change of time. That will give me the velocity, average velocity. When you apply the limits here, then probably we will have something which is instantaneous, right? If the limit tends to zero. So when we have, if I want to find out exact velocity, I just do this. In other words, it's exactly this, right?
Pawan, overleaf is free for everyone?
Huh? Yeah, I think everyone. It's free for everybody. So this is what we are talking about. The limit as h goes to 0, delta s per delta t would give us instantaneous velocity, whereas this is an average velocity. Just to distinguish, let me write this as capital V, or maybe a bold one. Okay. Is this clear? The Newton's perspective.
Yeah.
So he is a nice guy. So this is how actually he started inventing. But there is another perspective. So you know that you can apply this to, let's say, mixing of two liquids, growth of a virus, instantaneous speed, and all this nonsense. Like not nonsense, sorry. All different kind of stuff you can for sure apply. But now comes the idea of, in terms of purely geometrical sense. This one I really like it because this gives you a lot of insights, and you will be able to connect a lot of things together with the Newton. That's the basic idea of today. Okay, so now we are looking at a completely different perspective. As of now, don't connect with whatever I told till now about instantaneous velocity. Let's forget it for a moment. So the problem was something like this. Okay, so the mathematicians at that age wanted to calculate. Okay, but basically when in the Newton's age, there was no distinction between mathematicians and physicists. Everybody was same. Everybody was just trying to understand something. Okay, so now I have a straight line like this. Now I want to find a tangent to this curve. Okay, so the tangent to straight line is just tangent itself. So this is very trivial stuff. If I go back to the geometry of that 17th century, we probably had something like triangles, quadrilaterals, hexagons, polyhedrons, and all this. And the maximum we had was circles, right? So let's try to see how to draw a tangent to a circle first, so that we know what we're talking about. Aye, aye, aye. Okay, so now we have a circle here. Perfect, nice circle, amazing thing. So now we all know how to draw a circle, how to draw a tangent to this one. What we basically do is we select a point. Let's say at this point I want to draw a tangent. So now what we do is we make sure that there is only a point is connected and nothing else in the circle is touching this line, and those lines are basically called as tangent. That basically means if I draw a tangent, it should be in such a way that there is only one possible line where the circle intersects this one. The easiest way at that time was to do something like this: put a point on the circumference and draw a straight line. Okay, and the perpendicular to this, let's say if my point of choice is A, then perpendicular to this would be this with the tangent. The same way, if I choose, let's say, this point, what I do is I draw a straight line like this. Okay, and then I take a line which is exactly perpendicular to this line, 90 degree. The angle between EC and this point, this angle is 90 degrees. Okay, this is what they wanted to do, and this was very simple as well. And now the question was something like this. is it possible to find a tangent for something like this? Let's say x is equals to y is equals to x square. Very simple one, yet very complicated. He told, can we calculate? This was an open question. So now I give you, let's say, 2-3 minutes. Think about this and let me know. I want to calculate the tangent at a point, uh, let's say this one, x is equals to 2. Now, how do I write the how do I write the tangents to this line? Think about this for a moment. Think in terms of circles, because you're going back 1700 at that time, so you don't have calculus yet. The idea is to derive the calculus on our own. This was a problem. This was a problem. So now, can I, with whatever I know about circles, triangles, and etc., 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 can I calculate the tangent of this at this point A, or on any point on this curve? But let's try to find out what point.
This point on A, line passes through directly. It
That
just to
is,
touch to point A and after.
yeah, but I can, if your answer is right, I can also do the same thing like this.
But not Z.
Okay, I can, let me do it this way. No, okay, in that case, I have a conflict with this one. Okay, when you do this, there's only one point touching to the sine curve, but it's still not the tangent.
Not like that as 1 point touch. It is which point we want to find out tangent. Then this point
Let's say this
we
point. Sorry.
not like that. I can understand, but I don't explain.
Maybe you want to show us. You can share your screen.
I am logging to my mobile. I have some stuff with my laptop. So.
Okay. Okay. So, anyways, so the idea was given by somebody called as Descartes. I don't know. Yeah, Descartes. So he gave a very nice view of how to draw a tangent without using anything actually. So this guy is a genius. If you ask me. So he gave this idea of how to draw the tangent, but just with the circles and whatever. So open this one. So here we are. So I have a curve y is equal to x square. Okay, so this is a function. So I can draw any function here. Let's try to draw x square, which is our favorite one. So he told, okay, I only know one stuff, bro. The stuff is I know how to draw a tangent to a circle. So what he did is take any point, let's say this point, and then he draw a circle at the with the center on the x-axis in such a way that it touches only the curve once, like this. For example, if you want to see how, just move this point and you will see.
Brilliant.
Just move this point A. So this is how we created. So from the circle, this is just by pure luck. Just by pure luck, he found out this way. And when you go, it's extremely complicated, right? It's not a very useful way. But this gives us a very nice insight, basically. And then he told, since I have constructed the circle, what I can do right now is I know how to draw tangent to this circle, since the only point of contact between the circle and the function which has to be drawn is one single point. Then if I draw a tangent to the circle, that also has to be the tangent to the curve f of x itself. This was his view. And then, which is not false, this is absolutely right? So if you see, the tangent is exactly squeezed in between the function and the circle itself, and the tangent is both tangent to the circle as well as the function. And this was his view of Descartes. So this is a very nice insight, and there were a lot of people working on this. For example, Fermat is really one of the guy who changed the life of everybody. Okay, and he also gave an insight on how to draw tangents and all, and his insight was also very helpful. So I'm giving you perspective again. Remember this. Right now, the idea is to understand how the whole thing evolved. So this is a Fermat's perspective. Open this one. So in this, you can move this point x plus e. This one is almost very similar to the idea of Newton, but this is very geometrical because I am trying to find the how do you say, the tangent at the point, at this point, white ball. Here is where I am trying to find the tangent. Okay, so there's a something called slide me slowly. Please go ahead and slide it slowly so that you see what is happening. I give you some time. Okay. So now he just took 2 points, x and x plus e corresponding to f of x. He draw a straight line up, just touching the axis, and then he told, okay, I draw another one like this, s and e, and then I draw a circle, sorry, triangle out of this. Right? And again, if I do the same thing for this, it's again another triangle. If you have a good eyes, you would notice here immediately that uh, these two triangles are similar triangles, right? Both of them are similar. Let me show here. These are similar triangles, right? This is a very similar triangle. So he used the idea of similar triangle to draw the tangent, which is amazing. And then he said, okay, now I have f of x plus e, h, and this line is f of x plus, so f of x plus e minus f of x. And then this, from the point from this to this is the h, so which I can reduce or increase, let's say. Okay, so he told, if this goes to 0, then we can find the tangent. This is what he told. Nice insight, right? So by the way, if you have noticed, probably by now you would have got this one. If you don't, let me tell you, this is exactly what is the basis of all the numerical computation you do in your entire life. Take it or not, this is the basis for all the numerics you do in your entire life, including the Newton method, the conjugate gradient. I know somebody is very fond of conjugate gradient. I'm going to show it today, hopefully, how to come up with a conjugate gradient. And then the finite element methods, finite volume methods, finite difference methods, is everything starts from this insight of Fermat's, from the idea of course, calculus. Okay, we will see this in detail when we do something called linear approximation, probably today's class, at max next one, because I have a lot of things today. Is this clear about Fermat inside? Did we understand something today?
Yes.
Okay. Now, analogously, when we think about this in terms, in the perspective of the first guy, Descartes, then we have a problem. The problem is something like this. So for y is equals to x square, for sure this works, right? And then okay, even for this one it should work, but the problem is, let me show, we will have a lot of problems here. Let me show it nicely. Okay, so let's type this as cosine of x. This will give a nice insight into the geometry. Like this looks crazy, right? This makes me amazed. Seriously, this kind of stuff makes me really feel good because we are trying to connect a lot of things together now. And then see, this one is a really nice thing. So it works for everything actually. It works for everything. But one thing we were not sure about Descartes' view. Probably, if at all, if Descartes would have come up with a way to find the equation of this tangent, he would be the first guy to invent calculus, if you ask me. But unfortunately, he couldn't. And then he couldn't fix some of the problems, and we are going to fix it right now. The problem was this. So Descartes still thought that if at all, if we have a like he, because he probably didn't knew sine curve at that time, or maybe he knew, I don't know, he missed out somehow. So if I have a sine curve, there should be only one point touching the intersect, and then he was not able to contemplate the fact that ay, ay, ay. Okay, now look at this line. Okay, look at this line. In this case, this is what Descartes missed. He told, if there is if I can draw a circle here, okay, I would have a straight line like this, but this line is a tangent to multiple points. You take any circle here, and all of them are tangents to this. Like at this point, it's a tangent. At this point, it's a tangent. And even at this point, it's a tangent. So he was like little bit of worried about this behavior sometimes. So but he fixed it eventually anyways, but after Newton gave his insight, then he fixed this issue, telling that he added one more constraint to the problem, telling that if it is possible to have multiple points which are in contact with the graph, and they can still be a tangent to the graph. This was the only mistake he did, right? Otherwise, whatever the view last time we thought was absolutely perfect. The only difference is it is possible to have multiple points touching the tangent line of the curve, but still they are still tangent to the line itself. It is still possible. That's the only thing which was missing, and which he eventually fixed it. Okay, so this was the idea of completely geometrical perspective. Okay, now if you want to find out,
So
uh-huh.
can tangent intersect a curve?
Yeah, sure. We can always find such things. It can, but probably yeah. Let's try to in sines and cosines.